All right, this is 3.5 part 2, continuing talking about transformations. Today's going to be all about reflections. So reflecting across an axis, the graph of y equals negative f of x is the same as the graph of y equals f of x, but it will be reflected across the x-axis. So that is, if you have a negative number in front of your function, so that negative number is being multiplied by the function, the whole function, then it's going to reflect your graph across the x-axis. If a point xy lies on the graph of y equals f of x, then, so what new point is going to be on the reflected graph negative f of x? Well, you are actually multiplying the f of x by -1, which means you're multiplying the y by -1. So that's going to be x doesn't change, -y. So notice so far in yesterday's discussion and today's, if something is occurring outside of the function, it affects the y. If something happens on the inside of the function, that would be inside the parentheses or whatever function you have going on, it's going to affect the x value. So let's look at the x value. The graph of y equals f of negative x is going to be the same as the graph of y equals f of x, but it will be reflected across the y-axis. And that is still going to be affecting all of the x values. You are taking the x and multiplying it by -1. So if a point xy lies on the graph of y equals f of x, then the reflection is going to contain the point negative xy. And that's why those reflections across the x and y axis occur, because if you take each y value and change the sign to the opposite sign, then that is going to take that point and move it to the other side of the x-axis. While if you take a point and you multiply the x value by -1, then that will take that point and move it to the other side of the y-axis, thus giving you that reflection across the y-axis. Let's take a look at Desmos to hopefully see a better illustration of what's happening. All right, so I changed this to the square root function, whereas we were looking at absolute value yesterday. So here's the graph of our parent function for square root. It's not been transformed at all, shifted, none, reflected. Okay, so anyways, let's see what happens when I make my a negative. Notice a is in front of that square root function, and I'm going to just change this to -1. Okay, so notice as I did that, it slowly creeped across the x-axis and became a reflection of that original curve that we were looking at. So let me just move it back and you can see it reflect across the x-axis again. Notice each y value is just the negative of its original y value. Right, so I had 4, 2. When I move this to -1, I have 4, -2. So the y value just becomes negative. If it had started out a negative y value, it would become positive. Now let's see what happens when I change this b, which b is my value on the inside of the square root here. So that is inside the function being multiplied by the horizontal translation that we have here, x minus h, which right now h is 0, so it's not being translated at all. But I'm going to make b -1, and we should see a reflection across the y-axis. Lovely, there it is, reflected across the y-axis. So notice that each x value just becomes the negative of its original x value, and the y values remain the same. So for example, we've got the point -4, 2 here. If I move it back, I have +4, 2. Y value stays 2. x value goes from 4 to -4. Awesome. All right, let's look at some examples in our notes. Graph each function. So I've got the function g of x equals negative square root of x. That is a reflection across the x-axis. That is going to make you're multiplying the whole function by negative, so that's multiplying the y values by -1. So if you want, you could do like xy, each point xy is going to go to x comma -y. You're multiplying the whole y value by -1. So as I did yesterday, I'm going to graph the parent function. 0, 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Remember, you can get those points just by plugging in x values into the parent function, which is just the square root of x, and getting the y value. Square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Okay, then I can sketch that curve. All right, now to go from my parent function to my new function, I need to multiply each y value by -1. So if I do 0 times -1, it's going to stay right here. It's going to stay 0. That point doesn't change. Multiply 1, this y value 1 by -1. There's my new point. The x values don't change. This y value is 2. Multiply that by -1, becomes -2. And lastly, 3 times -1 is -3. So those are my new points. And there's my new curve. There is g of x. And notice how it's just reflected across the x-axis. When you have that negative on the outside of the function, it's going to reflect over the x-axis. All right, let's look at number 6. So now my negative is on the inside of the function. So that means that my points are going to go from xy to -xy. I'm not multiplying the whole function by -1, so I'm not changing the y value. I am only changing my x values. This is going to reflect your graph over the y-axis. Okay, let's graph the parent function again. 0, 0, 1, 1, 4, 2, 9, 3. And reflecting that over the y-axis, just making my x values negative. That doesn't change the 0, 0 again, but multiplying 1 by -1 puts me here, looking at my x values. Multiplying 4 by -1 puts me at -4. The y value stays 2. Multiplying the 9 by -1 gives me -9. Y value is still 3. My y values are not changing. I'm multiplying my x values by -1. Or if you just want to think of it as it needs to reflect over the y-axis, you can count from the point to the y-axis and then count that many to the other side of the y-axis. That's how reflections work. Okay, so there is h of x, and I want to label this one parent. All right. Now looking at a table. A function f of x is given in the table below. Create the tables for g of x, which is going to be negative f of x, and h of x, which is f of negative x. So the negative on the outside, that's negative y. You are multiplying each y value by -1. So right here for g of x, you could think of that as negative y. Now this one, they are literally, it's right there in front of you, f of negative x. So you are multiplying your x values by -1. So negative of the original x. So my first table, Also, let's point out that this is going to be a reflection. You always want to have these transformations kind of in the forefront of your mind. Reflect over x, reflect over y. Okay, so let's fill in our table. So the first one, multiplying our y values by -1, means my x values are not going to change, but my y values are going to be multiplied by -1. Keep in mind that if one of these numbers had been negative to start with, so let's say like -10, then over here I would have +10. -1 times -10 would give me +10. Okay, and the next one, reflecting over the y-axis, multiplying each x value by -1. You're just changing the signs of your x values. So -1 times -2 is 2. -1 times 0 is still just 0. We get -2 and -4. The y values do not change. All right, this page is a little different. We're going to be looking at the symmetry of functions. So a function can be either even or odd. A function f is called an even function if f of x equals f of -x equals f of x for all x in the domain of f. So basically what that's saying is the y values are going to be the same if you look at positive x and negative x. So if I look at, for example, f of -2 and f of +2, they should have the same y values. So what that ends up looking like over here, you can see on the graph, is it's basically it's like reflected across the y-axis. Each point is going to be symmetric across the y-axis. So its graph is symmetric with respect to the y-axis. And then for every point x, y on the graph, you're going to have -x, y also on the graph. So same y values, but the x values have opposite signs. And that is an even graph. So if it's symmetric across the y-axis, that is even. Okay, now this one might be a little more confusing, but it's similar. A function f is called an odd function if f of -x, so still plugging in that -x, equals -f of x for all x in the domain of f. It is, its graph is going to be symmetric with respect to the origin. And for every point x, y on the graph of f, you're going to have -x, -y on f. Okay, so let's talk about what all of this means. So if you plug in -2 again, that means I should get negative f of 2. Okay, so x was 2, so x is 2 over here on the right-hand side, but I'll have negative on the outside. So if I plug in the negative of that x value, I should get the negative of that y value, which is why you get the -x, -y down here. Now, let's talk about symmetric with respect to the origin. So if I have the point, let's say this is 2, 2. Then the point -2, -2, should also be on the graph, right? That's the xy going to negative x, negative y. So what you can think about with it being symmetric with respect to the origin is if you rotate this 180 degrees, rotate the graph, this line 180 degrees, it should be exactly the same. So rotate that 180 degrees. So that means halfway around, and it should look exactly the same. So you could take your paper and flip it upside down, and your graph should look exactly the same. So that's one way you can tell if a graph is odd or if it is symmetric with respect to the origin. All right, so let's look at a few examples of how questions about even or odd functions could be asked. So determine whether each function is even, odd, or neither. So to answer these types of questions, we're going to use these statements right here. So it's going to be an even function if you plug in negative x and the result is the original function. It's going to be an odd function if you plug negative x into the function and the result is just the negative of the original function. And then obviously if neither of those things are happening, then it would be neither even nor odd. All right, let's try it. So I'm going to do f of negative, not negative 2, f of negative x, because that's what's involved here for both of these definitions. They're plugging in negative x. So for every x that I have in this function, I'm going to replace it with negative x. Make sure you put that in parentheses. Okay, now let's simplify it. So I know if I raise negative x to the power of 4, that negative is going to go away. You could think of it as negative 1 to the power of 4, x to the power of 4. Well, negative 1 times negative 1 is 1, times negative 1 is negative 1, times another negative 1 is positive 1. So this is just positive 1. So 8 times 1 is just 8. And then I have x to the 4. So you see how if you raise a negative x to an even power, that negative is just going to go away. So same thing applies here. You could do negative 1 squared, x squared. Negative 1 squared is just 1, so that's just minus 3 x squared. Okay, now let's compare this simplified function to the original function. 8x to the 4th minus 3x squared. Notice that it's exactly the same. It is the original function. So what we see is that f of negative x equals f of x. Therefore, that is the definition of an even function. So this function is even. Now let's try that on number 9. So again, we're going to do f of negative x. Okay, so I replaced all of my x's with negative x, so let's simplify. Negative x squared is going to become just x squared. That negative 1 squared is 1, so it goes away. And then 5 times negative x is the same thing as minus 5x. Okay, let's compare that to the original function. Well, I see it's not the same, so maybe I'll try to see if it's an odd function. It's not the same, so it's not even. It's not f of x, so it's not even. So you could do a couple of things to determine whether it's odd. So for odd, you see that the whole function needs to have been multiplied by a negative. So you could say you could see what negative f of x is. It's going to be negative 3x squared here. Take this one step at a time. Negative times 3x squared plus 5x, which I can distribute that negative 1, and that's what I get. Okay, so if it's odd, it needs to be negative 3x squared minus 5x. Well, this one is positive 3x squared minus 5x, so it's also not odd. Another way that you could determine whether it's odd is you could factor a negative out. So if I divide both terms by negative 1 and put that negative on the outside, so think of it as like your GCF is negative 1, you're dividing both terms by negative 1 and moving that negative 1 to the outside, that would be negative 3x squared plus 5x. So just factored a negative 1 out. So that means that this would need to be f of x for it to be odd, because it would be negative f of x. But what's in parentheses is not f of x because of the negative in front of the 3. So this is neither. It's neither even nor odd. Okay, and that's because this does not equal f of x. That would be even. And then this does not equal negative f of x. And that's what it would need to be odd. All right, we've got one more like that to try. So we're going to do f of negative x. So 6 negative x cubed minus 9 times negative x. So negative x cubed, actually, let's look at this. We'll break it apart again. So negative 1 cubed is negative 1. So 6 times negative 1 is negative 6. When you have an odd power there, the negative will not go away. It will be part of the new function. And then negative 9 times negative x gives me positive 9x. All right, that is not equal to f of x, so it's not even. Okay, let's factor out the negative 1 like we did on number 9. So take out negative 1. That leaves me with 6x cubed minus 9x. It just changes both signs in there. And notice that that actually equals negative f of x. You got a negative on the outside, and then what's in parentheses is equivalent to your original function, f of x. So it's negative f of x. So because f of negative x equals negative f of x, this is odd. How odd. Okay, so that's how you can determine whether a function is even or odd. Now, let's look at some graphs. Number 11. So this is, remember, for it to be even, it needs to be a reflection across the y-axis. For it to be odd, it needs to be reflected or symmetric about the origin. So on number 11, clearly it's not reflected, symmetric about the y-axis. That we would have to have a piece here, and we would have to have a piece here, and then it would be symmetric, but then it wouldn't be a function, right? Vertical line test fails. Okay, so let's see if it's odd. So remember I said if it's odd, there are a couple of different things that you can see. But one of them is that you can rotate the graph 180 degrees and it will look exactly the same. So if you're good with visualization, you could probably do that in your head. If not, take your paper and rotate it. Just rotate it around. I think I can do that on here. And that looks exactly the same as it did before. So let me move it back. And you've got the exact same graph. We've got the curve in the top left quadrant, the curve in the bottom right quadrant, exactly the same as when I rotated it 180 degrees. So for that reason, this is odd. It's symmetric about the origin. Okay, let's look at number 12. So this one, let's see, even, reflectant across, it's symmetric across the y-axis. So this one actually appears to follow that, even though it's a kind of strange graph, just a horizontal line. But you can see that for every point that I have here on the right-hand side of the y-axis, I have a corresponding point on the left side of the y-axis. So it's symmetric across the y-axis, so this one is even. Now, look at 8 through 10, so not the graphs, but the functions. Do you notice a pattern for determining whether a polynomial is even or odd? So these are polynomials we were looking at. Do you notice a pattern for when a function ended up being even versus when it ended up being odd, or even on number 9 where it ended up being neither? So notice on number 8, when it ended up being even, the power up here was even. Oops. The power was even for the function, the degree. The degree of the polynomial was even. And when it was odd, on number 10, the degree of the polynomial was odd. But then why on number 9 was that not even, since the degree of the polynomial was even? So it turns out that the pattern is, in order for a function to be even, each of the exponents must be even. So on number 9, because we had 2 and then 1, that ended up being neither, because both of the exponents were not even. And then on number 10, we had odd and odd. So 2 odd exponents results in an odd function, an odd polynomial. Did I say 2 odd function? Anyways, 2 odd exponents results in an odd function. 2 even exponents, or 3 or 4, however many exponents there are, they all need to be even, and then it will be an even function. But on number 9, where we have mixed powers, we've got even and odd, that will be neither even nor odd. So just kind of an interesting pattern to notice, a little takeaway. All right, we will finish these notes tomorrow, looking at stretches and compressions and then putting everything together.